All right, so now let's do an example problem involving things like orbits and gravity. And we have this satellite that's sitting in orbit around a star at a distance of d. So this is the distance here, d. Um, Distance d. The mass of the star is capital M. The mass of the satellite is lowercase m. And we want to know if we moved it twice as far, if we moved it all the way out here to 2d, what would that do to the velocity? Would it need to speed up or would it need to slow down? So let's start with a free body diagram. Let's get in the habit of that every time. I'm going to throw this little curved line just so that when I draw the force of gravity, we can see very clearly that I'm deliberately saying this is a centripetal force. That's the direction it's going in. It's the force of gravity, but the direction is centripetal. And so writing a force equation from there, we're going to have the sum of the forces over the mass. But the type of force I have is the force of gravity. The mass here should be lowercase m like I wrote it, because we're talking about this object here that we're describing. So then we would have g m1 over m2 over, I'm sorry, I should do little m, big M, doesn't matter what order I do them in, over r squared all over little m. That'll cancel these. And so we get g times big M over r squared equals the acceleration. But this is a special kind of acceleration because it's moving in a circle. So that would be v squared over r. From there, we can just do a quick simplification step. We made the mass cancel there because mass doesn't matter. And we can get rid of some of the orbital radius there, but not all of it, which is actually good news because if it totally canceled, then we would be going about solving this problem wrong because we wouldn't have one of the variables we care about. Oops, that should be capital M, all over R. So now all I really need to do is just square root both sides. V equals the square root of G capital M over R. And then let's talk about the variables that we have happening here. I have capital G. But capital G is a constant. So if I move it to a distance of 2d, it won't change that because it's the universal gravitational constant. Universal kind of means it stays the same. So the factor of change there is 1 because it's just going from G to G. If I'm talking about the mass of this object, that should be lower. The mass of the star, I should say, or the thing that it's going around, it's still the same star. So the factor of change there is 1. But we are going from a distance of d, that's my r variable, to a distance of 2d. That's doubling that, which means we're changing that by a factor of 2. So when I go, now that I've figured out all of my factors of change that matter to this formula, I can say v is going to be equal to g is changing by a factor of 1, m is changing by a factor of 1, and r is changing by a factor of 2. So when I evaluate this, I get the square root of 1/2, which is 0.707. And that's how much the V is changing by. It's going from whatever V used to be to 0.707 times V. That means V would decrease as we get there. It needs to slow down. This is kind of counterintuitive. People usually expect the opposite result. They think you have to speed up to be further out. But really, the reason for this makes sense if we go through it conceptually, and everything should. If you're very, very far out, then the force of gravity is weaker on you. So if you were going faster, the force of gravity wouldn't be enough to keep you in orbit. And instead of you turning, you just end up zooming off in a straight line or kind of like spiraling your way out as you move your way out. Another way of looking, and if you're close into the Earth, then you have to be, or close into the star, then you have to be going really, really fast so that even though there's that strong force, you're constantly moving fast enough that you don't get like pulled into the center of the star. Last way to think about it though is if you were this satellite and the satellite was originally going in that straight line tangential velocity, it would actually need to push itself off in this direction. It's trying to, if it was like activating its thrusters or whatever to try and change its orbit, because it needs to slow down so it won't deorbit, but it's also trying to move itself further out. So you can see it moving outwards, you have to also slow down in order to make it work. If they moved straight out this direction, they'd deorbit. And if they moved that direction, they were speeding up and pushing away, then they'd actually just zoom right out of orbit and just leave the orbital system entirely. So That's the satellite example problem. Hopefully it now makes sense from a mathematical and conceptual basis. Thank you so much for watching and have a great weekend. Bye.